Yeah, sure. Yeah, thank you, everyone. First of all, thanks to the committee for inviting me for giving a talk on condition monitoring of electric motors in electrified transportation. My name is Adil Usman, and currently I am working as a researcher in National Renewable Energy Laboratory, which is a part of US Department of Energy. And I am located in GOLN, Colorado, which is in the United States. And my background is on electrified transportation. I work on the design and diagnostics of electrical motors, which are used for electric transportation, which could be on the land, it could be on the marine, it could be on the electric aircrafts as well. So today's presentation will be dealing on the uh, monitoring of the health of the state of the motors, which are used in electric transportation. So I will be covering the following contents, which will include the introduction to the electric vehicle. What is electric vehicle? What is comprised of? Majorly, it is of two parts. One is the power unit and other one is the mechanical unit. So power unit includes the batteries and the mechanical unit includes the electric motor. So that will be the focus of today's presentation. Then I will be discussing some motors employed for electric transportation. As we know, like it's a era of where everything is changing from IC engines to the electrified transportation. So we need to see what types of electric motors are employed in those transportation system. Then we will be seeing some health monitoring techniques which are used to estimate the health of the motor while it is under operation during the working of any electric vehicle. Then I will be telling some state of health estimation based techniques, algorithms, and also emerging techniques for condition monitoring of drives. So these will be the focus and starting with the introduction. So, electric vehicle is usually used for driving purpose. It's a mobility mode of transportation. When we talk about electric vehicle, it means our gasoline, our IC engines are replaced by something which is electrical, which does not employ any gas, petroleum, diesel, or any source of non-renewable energy. It is something related to the electric part. So as you can see here, electric vehicle combining mostly of two units. One is the electric motor, which usually is termed as mechanical part, and the electric battery packs, which is commonly referred as power unit. So they are not limited to road, as I mentioned already. It depends on the surface water, underwater, electric aircraft, and electric spacecraft. So today's presentation, I will be discussing on the motors which are usually used for these applications, which includes almost all. And if at all there is a fault in a system, if at all there is a breakage or a failure in an electric motor, how fast you will be able to diagnose it and estimate its state of health, that I will be discussing in my today's presentation. So why we are going, first of all, why we are going for electrified transportation, why we are transitioning the complete system. As your conference theme itself says, it's a fourth industrial revolution for emerging future. So almost emerging future has already started now, taking the shape. You can see around yourself how much system is being changed and transformed into the electrified transportation system. So it is because of the carbon dioxide emissions, which you can see here as a graph. Uh, different countries and the continents, how much per capita metric tons of carbon dioxide emission they are doing, that is mentioned here. In order to reduce these things, we are actually transforming the system from carbon dioxide emission to zero carbon emission. So that is called decarbonization. So majorly why carbon dioxide emissions we have to take care for our vehicle, just because most of the carbon dioxide emissions are usually reduced by the vehicles what we drive. So that is the reason we are actually changing the system of the complete transportation, making it electrified, so that we will be in a major aspect, we will be declining the content of carbon dioxide emissions in the environment, which itself eventually will be not affecting the ozone layer and also global warming. So things are related to each other. But the thing is, if the primary focus, if we try to change and monitor, then we are able to change the end product. Going further, alternate solutions. When these carbon dioxide emissions we have to reduce, you can see in the number of vehicles on the road almost every day, I mean, I know the situation in Bangladesh as well. I'm aware about, because I'm also surrounded with the people around me in my company. So we know how much the traffic and the pollution is going. It is like all directly related to each other. So the thing is electrified transportation, but that itself is going to reduce the carbon dioxide emission, but it does not going to reduce the traffic. So my content is not related to the traffic, but to the carbon dioxide emission. So when we are going, so these are the some common examples. You can see electric cars. We can see there are some personal e-scooters which are also being used now. They are using actually the solar charger. They are using for charging it. You might have seen in some of the countries, including yours, where they are having this system in the parking slot. They have some online application where you just book these vehicles to drive personally, and then you can stop into the other stop, and you can park it over there, and you pay the required amount what you have to use. Then these are battery electric buses, which are majorly used now in most of the developing South Asian countries. E-scooters, which are very common in the universities and the colleges now, and personal e-transport. So as I see here in the United States, people are having their own personal e-transport where they used to carry their own stuff rather than hiring some e-haul or some trucks for carrying their objects and products from one place to another. So these are some of the examples of electric transportation. So further, when we move, we think like electric transportation is something like it's a new concept, but eventually we forget that this system, this technology has been already been done, established a century ago, not even some decades, but century ago. It was based in Detroit, which is a capital city of Michigan State, which is in United States, and it is also sometimes called as the automobile hub, because most of the automobile companies have their own factory outlets over here, and it is called Automobile City. And this city was actually a century ago. They had started this electric transport cars system. It was well established. They used for certain period. I mean, as I see, you can see here, the company built almost 13,000 electric cars from 1907 to 1939. So almost 32 years the manufacturing was there. There are still some cars, electric cars, which are put in the showroom as a demo for the people to visit in the museum and see. And there are some cars which are still used. Sometimes you may refer them as a vintage car. You see most of the people of the ancient, like very old time people, they are having these as their antiques, and they are still functioning. So this is not a new concept, but it is something like we are again reviving it, revising it, and revitalizing it, and bringing them in today's generation, in today's world, because of the need of the hour. Moving ahead, I just wanted to mention about some of the electric car companies. If you might be familiar with these, like Tesla, I think most of the people know about it. But there are some other companies which I wanted to bring into your notice. That this is like Bollinger Motors, SF Motors, Faraday Future. These are the companies which are, I cannot say these are the very old, but yeah, in competition to the Tesla, they are very new companies which are actually manufacturing the electric vehicles. And it is not just a manufacturing, they are also deployed on the roads, like people are driving it. And further, if you see some more, this is Rivian, Lucid, and Fisker. These are actually the companies which are taking the market, and especially in the west of United States, which is the California state, where they have this manufacturing unit. They have their products means manufactured, and they're also being driven in these areas. Not only in these areas, but across the country, they are being driving. They are like very new, but in fact, they are like almost well established now, because people are taking them into the market now. They are commercialized. So moving ahead, now I just wanted to again brief you about what makes a difference from the conventional electric vehicle automobile to the electric vehicle which we are using. It is just like gasoline is replaced by the battery, and the IC engine what we used to use is replaced by the EV motor. When we both combine together, we form a electric vehicle. There could be many other components and integrated part as well, but these are the major focus where our research and R&D depends upon. Moving not into the battery management system, but on the electric motor part, I just wanted to highlight in today's presentation, what are the electric motors what are used in electric vehicles. So these motors could also be used in your conventional automobiles as well. But for the electric vehicles, electric motors, electric drives, these are the motors which are usually preferred. So when we talk about like electric machines, usually we talk about AC and DC. So let me tell you, these both motors are AC motors. And within the AC motors, again, we try to categorize. They are called as synchronous and asynchronous motors. So when we talk about the asynchronous motors, it is actually induction motors which are usually used. Tesla is using these motors in their cars. And another one is synchronous motors, which is not like an asynchronous. It is means that the speed of your motor or the output the speed of the motor synchronizes with your input supply frequency. So these are termed as synchronous motors. So these pictures, what you can see here in this slide, are the actual motors which are used and employed in the electric cars. So among the synchronous motors, if we talk about, there are again two types. One is the permanent magnet synchronous motors, and the other one is brushless direct current motor. Both the motors are permanent magnet. Both the motors are almost have the same principle of operation, but the difference comes in the back EMF. So back EMF is important when we are deciding the speed. So when we talk about the PMSM, it is a sinusoidal waveform, as you can see here. And when we talk about the BLDC motor, it is a trapezoidal waveform. So sometimes we club this motor into one name and we call them as brushless permanent magnet synchronous motors. So today's presentation will be telling about these motors condition monitoring, because these are the vast emerging motors which are used in these electric car companies, which I showed you in my earlier slides. So just going into the internal structure, just now from here, the presentation could be a bit technical, but just let me know if you have any ambiguity or questions or concerns during the presentation or after the presentation. Anything is fine. So just going just going ahead with the motor architecture. So you can see this is the practical motor, what is on the right hand side, and this is the internal architecture. So as we talk about motor anytime, we always refer to two things. One is the stator and the other one is the rotor. So this is the stator, which has the windings, which you have a control to excite from the inverter. And this is the rotor, which has permanent magnets. So this is actually the one which rotates. This is the rotating part of your machine or a motor. So when this rotates, your shaft rotates, and your shaft rotates means the wheel of your electric vehicle rotates. So actually, we are providing mechanical energy to your electric vehicle. So this is the complete architecture. So now, if we talk about more practical motors. So these are the practical motors. These are the real pictures taken in the laboratory test bed. So these motors are exactly the same motors which are used in these electric cars. So if you see these are the motors which have been like opened by us in our R&D department, and you can see how the architecture looks from the outside. This is the outside motor, and this is the another type of motor. Both are BLDC and PMSM motor. And when we open, we see the stator architecture, we see the windings, and on the rotor, we see the permanent magnets. This is another rotor for this motor, and we have permanent magnets on the surface. So when we talk about the condition monitoring, like these motors are actually integrated in an electric vehicle, and their operation is like you never see. It's like a black box. They're running and your vehicle moves. But what happens if there is a fault in a system? What happens if something goes wrong in the motor? So the main motivation of showing you this picture was, if anything happens in a motor or in a machine, it could be probably in these parts only what you are seeing right now. Either it could be on the stator windings, or it could be on the magnets, or it could be on the bearing. So these are the major things, major you can say physical source where the faults can happen. So the motivation of showing you this is like when we know when these things goes under fault. Let's say if this goes short circuit, these two windings get short circuited, then there is high flow of current, and then there will be a faulty current, and there could be a fire, and the windings may burn. Let's say if this is a magnet and if the magnet breaks, then it could be a fault in a system. So when I will be discussing these aspects in the future slides, you will be able to visualize these pictures and get to know how the fault in a machine could happen. when a machine is under operation under abnormal conditions. So these are the I can tell you it's like a finite element method. So when we actually do something, when we diagnose or analyze any machine or any system, we always try to go first through the simulation wise. That is something called mathematical tool. So we have developed and designed the same machines which you saw in the previous slide. These are the same machines which is having now Flux model, which we did using ANSYS Maxwell software tool and COMSOL and Flux tool, which is called Altair Flux. We use those mathematical tools because they are very accurate, they are very reliable, and they actually give you the performance of the machine, which actually matches with the real-time performance. So we design the physical architecture of these motors in order to see its performance in terms of current, back EMF, voltage, speed, and torque. Because these are the parameters which ultimately define the performance of the motor. And these are the only parameters which changes during the effect of fault or any mishappening in a machine. So again, those motors are here with the controllers because whenever there is a motor we are running, we need to have its controller. So these are the market available commercialized controllers what we have used in order to drive those motors. And these same controllers are also used in your electric cars. So again, you can see this is the integrated system which I tried to show you. Like, let's say this is your electric car, and in an electric car you are having a battery. So battery is like something people are very much familiar, like it's a battery car, so battery will be there. But ultimately that battery is feeding your mechanical unit as well. So when that battery management system feeds your mechanical unit, that mechanical unit, which is a motor, is actually coupled with an inverter. So that inverter is getting the input voltage from your batteries because that is the only main power source in your car. Then the complete system takes its routine way of working. It feeds the motor. Motor gives the output in terms of currents, position, speed. It is fed back to your controller, which is like a black box. And again, the healthy operation of a motor evolves. So it keeps on running. It's like a complete integrated system with the first part called battery, second part with motor. But this motor is actually with the control and the inverter. So this is the complete system which is in your hand now. So we want to see like what types of control are there. So we know there are like various controls available: hysteresis, vector, period-oriented control. Any of the control technologies can be applied for the effective running of the motor. So the main point here is like I just wanted to show you when we are diagnosing a motor. It is not like randomly we are diagnosing a motor. We are actually trying to mimic and replicate, develop, and design the complete control system along with the integrated battery and motor to run a motor as if it is running in an electric vehicle. And then we try to emulate the faults. So just to in order to get the real feeling, what happens actually in a electric vehicle or electric car when it is operating, and suddenly a fault happens. So this is the complete system which undergoes into the diagnosis. So this is the healthy operation system. So yeah, I already mentioned about the integrated system. So this was the slide which I was mentioning earlier. So this complete system is how it works. You have an electric car. Electric car is having a wheel. Wheel is coupled to the motor. The motor is coupled. And the motor is having the complete integrated system with the inverter, controller, and since it's like feeding back the speed and the current in a closed loop, so it is being fed. This inverter is fed by the battery management system. So this is the complete integrated EV motor drive system, which is actually being used practically in any of the electric car which is in operation. It could be local or it could be at a national or international level. Things would be just advancing in terms of its features and capabilities, but eventually the system and the integrated system remains the same. So what about the importance? Like why we want to monitor it? Like we designed the motor, we designed the battery, we designed electric vehicle, and everything is like functioning. Our motor and electric vehicle is running now on the road. So what is the importance of condition monitoring? So the condition monitoring, the importance is because anytime a fault can happen in a motor, we never know. Fault is something which could happen in the physical geometry of your motor. It could be a short circuit, it could be the breaking of rotor permanent magnets, and the winding short circuit, open winding. So these are the faults. So when it happens, what is the first thing which will affect you? First thing is the motor will be under the fault. It will be like having the burning of the windings. It could damage your integrated system, which is coupled with that motor, let's say like a battery or inverter. And again, the very important part, your electric car or your electric passenger car is having people inside as a passenger. So life is the major important aspect which we want to look about, because we want to prevent the life of the people and the property as well. So that is the reason we always want to monitor the state of health of a motor and also the batteries whenever it is under operation. So conditions leading to motor fault, what could be the conditions? What can lead to the faults? One thing is very much obvious to you as well. It could be the environmental and physical stress, because the temperature changes sometimes, and also most of the times the permanent magnets what you are using in the rotor, it ages, because let's say you bought a car like 5 years ago, and we never know the motor what is used in that car. Minimum it will be 5 years old because you bought it, and when they bought those motors and used in your car, you never know. So the age of the motor decides the age of the permanent magnet as well. So you never know, and with the aging factor and the aging parameter, the physical strength of the permanent magnet or any material will change. It will become weak. So those things actually are the major causes of the faults. And also, most of the time, like let's say we talk about the passenger vehicles, they're continuously operated. Most of the time, like I come from the mountainous part where we use electric buses and electric cars sometimes, but the electric buses, imagine how much load they are taking on the mountains and then they're coming back. So they have other effects of regenerative braking as well, and there the conditions become very sensitive, and it can be prone to the effect on the motor or machine of your car. So I have defined fault. Fault can in a machine can be anything which is not normal, which is actually deviating from its normal condition. That can be called as fault. But how can we see the effect of fault? If a fault happens, what is the first thing which will bring a change in your system, which you can see by your own? So first thing, what it brings a change, which is very much evident, is a change in the current and voltage. What is something which is in our control? We can see those things. These are the parameters. We can have a data acquisition system to monitor and acquire the data for these. Another thing which will go into more R&D and research into details, it is like magnetic quantities like flux, acoustic noise, vibrations, because whenever there is a fault, you see there is some humming sound, there is a vibrations, and there is acoustic noise in the machine, which makes you evident that there is something fault has happened in a machine. That's why it is sounding so much. So these are the characteristics which are evidence during the time of fault. And if these quantities only if we monitor, if we diagnose, then it is very much sure like we will be able to estimate the state of health of a motor. So these are the signatures what in the scientific community we use: motor current signatures, back EMF, flux, thermal analysis, acoustics. So these signatures, if you are able to get out of the get from the machine and continuously monitor these data, then anytime when these data are not matching with the healthy performance or the reference, then we can predict there is a fault. So these are the real-time uh, results which we have taken during the fault and during the healthy operation. So let's say the motor which I showed you earlier, it was running under the healthy state. So you can see we have a motor current in the left hand side, then we have motor back EMF. Motor back EMF actually decides the speed, and then we have rotor flux density. So flux density we have taken here because we are dealing with the permanent magnet motors. So flux indication is very much important. Now we see if we have a fault in a motor. So whenever we have a fault in a motor, these parameters will be changing. But before we go into the fault, I just wanted to bring one more point: how we can diagnose those faults. So these are the diagnostic techniques I actually mentioned in my talk, but just briefly telling, these are the some conventional techniques which are used: analytical method, magnetic circuit method, numerical method, which they use to diagnose the fault whenever a fault happens. So limitations, why we want to like to see like what are the limitations of the existing fault techniques. Because of the accuracy, time, diagnosis speed assumptions, we are not able to diagnose the system in a proper way. So we come with a new method of diagnosing the fault. So we have combined some of the existing methods to develop our own time efficient faster method which will be able to diagnose the state of a motor in its initial stage. Like when the fault is just about to occur, our system should be able to tell that there is a fault. It should not tell when the fault actually has happened in the machine. So ultimately, there will be no use when the fault has already happened in a machine. So these are the some diagnostic techniques what we have developed and established in order to see the condition of the motor while it is under operation. So you can see the earlier state of motor currents. It was like same. You can see the blue one. It is the healthy motors. And whenever there is a fault, you can see the red one, which is like a fault condition. Similarly, for back EMF and flux and plug density, we see the performance of the machine is not exactly what it was during the healthy operations. So these changes in the characteristic performance eventually tells that there is something wrong in the motor, which is ultimately the fault. So then using those techniques, what just I mentioned in between the flow, which was like fault diagnostic techniques, we could be able to measure the state of health of a motor. And state of health of a motor could be judged or could be analyzed with the motor characteristics features, which is back EMF, flux density, and motor fault currents. So you can see how the performance changes here. As you see here, the change in the motor back EMF is from the lateral side of your half loop. But here, when you see the plug density changes, uh, it actually reduces. It is not from the side. So these different characteristics and observations will eventually tell you what could be a fault. I mean, here, if it is a breaking of a magnet. It's a physical damage of a magnet. But here, if there's a decrease, then it means the property of the magnetic material has reduced. So there is a difference. Within the fault also, there is a difference. So that we call as fault classification. So that we can only get to know when we have different types of fault occurring in a system, and when we analyze and investigate each fault individually. So this is the methodology behind how to diagnose the fault in a motor, how your system works, how its state of health could be established. And same algorithm, just I don't want to go more into the detail. So same algorithm if we use, and we can develop an online condition monitoring system. So this is something which is called technology to market. So based on the different characteristic curves, data, what we got under the various fault conditions, we develop an algorithm which could be used for online condition monitoring. Same algorithm we just used in our system just to get the fault. So whatever the fault will be there, just we see the flux parameter, we see the motor back EMF parameter, and we see the current. The moment we see these characteristics, we will be eventually be able to tell what type of fault it is and what action needs to be taken. So these are the field analysis related to the flux I wanted to mention. So yeah, so this eventually that online condition monitoring system what we develop could be in a graphical form. So first graph, if you see, it's like a healthy state. There's nothing wrong in the in the characteristic feature. So this is called as a reference profile. The moment there is a fault, there will be some change and intercept in the stator phase current and the motor back EMF. So when we have these Lissajous figures with ourselves in our online condition monitoring system, we could be able to tell what type of fault it could be. So when this pattern occurs, we will be able to tell it's a lateral partial demagnetization, means the magnet has just started to demagnetize. It is not fully demagnetized. This is something called radial demagnetization, means from both the ends, your magnets start demagnetizing. And that, then the very unique and unusual behavior, it shows the breaking, means it's a physical damage. So these figures we have developed using the data of the motor under various conditions, and then we are able to develop a technique so that it could be employed in our practical electric cars and electric vehicles, which are actually being driven on the roads, but their condition monitoring is not being done. So what if the fault happens in an electric car, in an electric motor, which is employed in an electric car, but we never know about it. So this is something which is like uh, established by our R&D sector, and we are able to employ these to the companies so that while they are manufacturing the cars, they could also have something on their speedometer, which could just able to on a speedometer, which could just tell the state of the motor in terms of back EMF and flux. So this was the end, and the key takeaways from today's presentation was like emerging trends in electric transportation. What I wanted to highlight. The importance of electric motors, because they are the major source for the electric vehicle to be driven, because they are the mechanical part. Health monitoring of EV motors, it is important in order to save their life and property. Then different types of fault diagnostic techniques, what we employ to diagnose the health of the motor. And finally, we implement those in order to estimate the health of a motor, which is eventually estimating the health of the car. And then finally, online condition monitoring system, which is like a technology to the market, what we have implemented. So these are the advanced fault diagnostic techniques, which I just wanted to mention just through one slide. Apart from flux, motor voltage, motor current, and motor voltage current back EMF, there is something new emerging now in terms of acoustic noise and vibrations. So we are actually dealing with these also as well as of now. And just based with the frequency and amplitude performance of the machine physical state, we will be able to tell the types of fault in a motor. So that is for today's presentation. And yeah, thank you so much. And I will be happy to take if there are any questions from your end. Yeah, thank you.
Thank you very much for your excellent presentation, and we really appreciate your time for us. Now I'd like to open the floor. If anyone has any question for the speaker, please. Okay, I think we don't have any question from feedback from the participants. We have one question from Cecilia.
Hello.
Hi, Professor Seeley.
Dr. Can you hear me?
Yeah, I can hear you. Hi. Hello.
It's late tonight, but the participants here, the presenter after you came and done late, so they have the session chairs that ready. So anyway, I was in our session and I listened one part of the presentation. Could you please explain that to do this type of research, the young students who are sitting here and we presenting paper, what skill and what preparation they should know? Because we are really focusing on soft computing, like computers, computing, machine learning, deep learning. But to do your research, what preparation and how they create their background? You can just give them in the layman terms how they will prepare themselves.
Professor Celia, as I mentioned already, like there's some issues with the voice, but as I could understand what you meant is, how can I tell your students how to prepare for the research background for their research? That is what you are asking, or you want? And also, if you don't mind, you can just type some keywords in the chat box. I can see.
Can you hear me?
Yeah.
Telling because it's not your research is not depending on computing, it depends on design and analysis. That the young students, how they will prepare themselves and what background, what mathematical and what type of background they really need to create a passion for such type of research rather than going to the competition.
Okay. Yeah, got it. Thank you. Yeah, so that's a very practical question and also very beneficial to the students. So as far as I understood your question, what I can mention is, see, whenever we have any research problems, there are plenty of solutions for that research problem. Let's say we are transforming everything to electric vehicle. As an electrical engineer, for me, the main part is focus on the electrical side of the electric vehicle, which is like a motor or a battery, right? It is related to electricity, power, voltage, flux. For a computing side, they have vast application. Computing is something they can go anywhere because everywhere we require computing. So if you just saw my last slides where I was having the some results, right? Yeah, some results was there. There actually I have used the computing software tools. I mean, when I submitted my PhD some years ago, 2 years ago, the future of my project was actually an application for the computing people. It was like machine learning. You can imply machine learning over here just to get the data. And your computer science engineering will be the most appropriate people just to predict the fault well in advance. I am able to predict the fault, let's say 5 to 10 minutes before. Computing people can forecast just one day before, 1 week before. And that could actually be something very, very much relevant in today's time where every country is moving into electric transportation. So definitely when they are moving into that, they need this data. How fast people can evaluate that data? See, I designed a motor and the data will be given out. But who is able to collect that data? That is computer science people, information science people, machine learning people. I am on the electrical side of the background, and I am going into the core of the motor, material, winding, rotor, permanent magnets. That is not the job of the electrical science people. They should know what data is coming. Let's say a voltage is coming. What is the voltage at every second? What is the characteristics of the electric voltage? How can they do Fourier transformation? That is something related to the signal processing. How that signal is communicated to the user, that is communication science. When I in the last slide I mentioned about the vibration and sensors, that again it's an open focus, it's an open scope for the people working on these sensors. In fact, I wrote a proposal in the US Department of Energy of monitoring the state of health of your electric cars using sensors, where you will be removing your data acquisition system of voltage source, oscilloscope, everything. Just use small sensors, current sensors, use voltage sensors, use vibration sensors. Those sensors, what data they are giving, again, it is opening a source for data science people. Anything which is giving a data, computer is required, computer science people are required. We need to have a data for the weather forecasting, right? So again, the data is required. All historical data. The data what I used in my system, as I showed in your presentation, is not the historical data of someone else who did it. But I did everything from scratch to this level. Now, if somebody from the computer science wants to do something, he can take the data generated by me. He can use his own algorithms. He can put his own techniques in order to evaluate the state of health of a motor. And trust me, let me tell you, like as a research, we do everything very conventionally. But ultimately, when things transfer from technology to market, everything goes very, very in a compact box. You know what I mean to say? It will be just commercialized in just a system, just put a button and the user should be able to see the output. What is going in the background, nobody bothers. So what the user is very much interested to see, that is something can be done by the people who are working on the computer science and information. Yeah. I hope, Celia, I was able to answer you. Yeah.
Okay, thank you again. Thank you so much for your valuable time. We really appreciate your time. So we have to end this presentation and we'll move forward to the next. Okay.
Okay. Yeah. Yeah. Thank you so much. Thank you. Thanks. Take care.
Assalamualaikum. Thank you, Adil. We enjoyed your presentations, but this presentation is very much important at the present time. But it is a demand of present time because alternate fuel, and also the carbon emission is very much important in present times. So we are very much grateful. At deep night, you are presenting your papers. So thank you again very much. Thank you.